Hi everyone. So today we're going to continue on our discussion on 6.2 chain rule. And from yesterday we learned that the chain rule for a composition of two functions that have several variable vector value would have to be a product between the derivative matrix. And if you think about it, it totally should not surprise you, because if you think about it, it's basically the concept here. See, from the beginning, when you learn chain rule in BC calculus, both functions are single variable generating one single real value, and the derivative of a composition is just a product multiplication between two scalar, which would be f prime of the g prime of f of x and f prime of x. In 6.1 chain rule, both the f and g has a vector derivative. So therefore, the chain rule basically is saying that we have to dot product the two vectors together. And now in 6.2, we have two vector value functions of several variable, and the derivative are matrices. And therefore, chain rule dictate that we have to multiply their matrices together. So it's a natural progression. And if you think about it, a scalar is a one value vector. And then when you have a vector is like a column or a matrix or row of a matrix. So therefore it scale up to what we talk about right now, several variable function vector value. Now, what I want to show you today is the concept that what if we have two function f and g that have multiple independent and dependent variable? That would generate an extremely massive matrix multiplication that would could be an end result of a large derivative matrix for the composition. But if you recall what I mentioned in chapter 5 when you first learn about partial derivative matrix, is that we actually don't usually use the entire derivative matrix. And more likely we'd be using some part of it, or maybe even just one specific value within the derivative matrix. And if I only want one value within a larger matrix, it seems kind of pointless to try to generate all of them. So therefore, it says some way that we can identify a single specific value within the derivative matrix and just generate that one single thing without everything else. And of course there is, and require you to understand what's going on. So let's try to take apart what's happening. So I'm going to use one of these examples. Maybe we'll just use this example that we did before. So in this example right here, we have a function f of t, which is equal to t plus 1 e to t. We have which equal to e f which is uv. We have a function g of uv, which is equal to u squared plus v to the third uv, and that's equal to xy. And remember, we can define now a composition h of t that give us xy directly. Okay, so therefore in this scenario here, we take t through the function f to generate uv, and then through the function g generate xy, and the composition kind of directly relate t with x and y. Now that is important because of the following. If I strictly look at function h as its own individual function, meaning somehow if I can manage to combine f and g together into one single formula, then that formula would directly allow me to define x and y with t. And if that is the case, that means now I can consider h as its own function with one single independent variable, t, and two dependent variables, x and y. And therefore I can talk about h prime of t as if the derivative of the function h with respect to t. And based on what we learn, that implies what we're looking for in this case is dx over dt, dy over dt, which turned out to be what we found out from yesterday. So this implies that dx over dt should equal to this thing, and dy over dt should equal to this thing. Okay, so That's fine. Now comes the big question. Can I only generate one of these without worrying about the second one? Is there such a way that we can actually do that? Well, of course there is. The idea here is the following. The idea here is that if you look at the partial derivative, notice that this partial, the dx over dt, this partial derivative relate x with t. And this dy over dt basically relate y with t. As a matter of fact, dx over dt basically means change in x over change in t, or the way I like to write it, and I strongly recommend that you do write that down for yourself, and this is how you should think about it. Dx over dt basically tell me how t changes x. And what dy over dt does? How t changes y. That's what the derivative is telling me. It's telling me how a single independent variable changes a single dependent variable. That's how all of these derivatives are going to work. So now comes the big question. Can I somehow find out how t would affect x? Of course there is. The idea rests on something that you remember learning in BC calculus, of course. In BC calculus, well, actually, maybe I state the question first. So the question is how to find one of these derivative, which eventually they become partial derivative because we could have multiple independent variables. So I'm going to go ahead and state that, even though in this particular example it's not a partial derivative. How to find these one of these partial derivatives without generating the entire derivative matrix. That's what we're trying to figure out. And the way to do that is start from BC calculus. Now, if I remember in BC calculus, obviously you learned the chain rule to be this. Basically equal to h prime of t, well actually maybe I'll write it like this, g composition f prime of x is equal to g prime of f of x multiplied by f prime of x. So that's definitely what you remember learning, but some of you might recall, and I'm hoping, I do believe that Mr. Ambrose as well as Mr. Stewart must have taught you guys this, is that there's a second way to write chain rule using the d over dx notation. And if I'm not mistaken, the second way to write chain rule is this. We're going to let f of x equal to u and g of u equal to y. Then the composition h of x would equal to g of f of x, which is equal to y. So therefore, h directly relate x and y together. So therefore, I can now define h prime of x would equal to, technically speaking, dy over dx. Why is it dy over dx? Once again, think this way. Because h define the relationship between x and y, therefore the derivative would tell us how x changes y. That's why I call dy over dx. Okay, it's the bottom variable, which is the independent variable, how it changes the upper variable, which is the dependent variable. So in this case, dy over dx basically read how x changes y. The problem is because h is formed by a composition, x does not change y directly. So how does it work? Well, it works this way. Y would get changed by u, but u get changed by x. So if I kind of combine those two changes together, I will now know what happened to x, how x changes y. So if you read this, you have to read it from right to left, and you read it from bottom to up. First, you read dy over dx, which means how x changes u. And then you read dy over du, which is how u changes y. So therefore, in this case, you can now identify how x changes y through u. The way it works is the following. Is first x, and then we talk about du over dx, which tell us, maybe I'll write it this way. So we have x, and then du over dx tells us how x changes u, and then now u would then in fact change y, which dy over du tell us how u changes y. So when I chain them together, which is why I call chain rule, I can now talk about x changes u, which then changes y, by combining du over dx and dy over dx, dy over du together. Now that concept now become an important part in what we try to do. What if now what we have is a similar scenario, but our f does not go from R1 to R1. Our f go from Rn to Rp, which is our function f of vector x equal to vector u. And then we have g that map from Rp to Rm, which our function g take in vector u and give our vector y. Now, if you look at these two statements compared to what we wrote before, it seems like all I need to do is put the arrows on top. So what's the big deal? Well, it is a big deal. The reason why it's a big deal because now what happened is the following. This basically implies f of x1, x2, to xn would equal to u1, u2, to up. And then this bottom one tell me g of u1, u2, to up would then equal to y1, y2, to ym. So now, in this case, even if we don't count the u, vector u, we will have n variable of x and m variable of y. That makes for n plus m that many variables going on. So now comes the big question. What if I want to find a single variable x sub something and how it reflects a single y variable, meaning the following. How to find dy sub I over dx sub j. What if I want to find how one of the x variable changes one of the y variable? How should we actually calculate this? Well, the answer is simple. We use chain rule. But the problem is it's a little more complicated than the chain rule that we have right here. Notice in here, we have x changes u changes y. So this tells us how x changes u, du over dx, and dy over du tell us how u changes y. And when we multiply them together, that tells me how x changes u, which then in turn changes y. Now we have the same scenario, except is a little more complicated because of more variables involved. So let's see if I can draw you a good picture to kind of show you how this works. Okay, I'm going to try to draw a really big picture so that I can put everything in to show you how that works. So hopefully it's not too confusing. All right, so here comes the idea. So in here, the idea is that we have vector x. Okay, vector x is actually x1, x2, to xn. And go through the function f, it turns into vector u, which is u1, u2, to sub p. And then go through the function g, it finally arrives as a final output, y1, y2, dot, 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 y sub m. Where n, p, and m could all be different or the same, we don't know. So now comes the big question. What if somewhere here I put in a variable x sub j? I want to know if I change this one variable while every other variable stays the same. Okay, we're not changing any other variable, but just changing this one single variable. Okay, how does that affect one of the variable over here, which is, let's say, y sub I? Oh, actually I use red, so I'm going to use red here. Y sub I. So now my question is, what if I make a slight change to x sub j without changing any of the other independent variable x1, x2 to xn? How does that slight change to x sub j would have what kind of effect on only the variable y sub I? Well, now make sure you understand, if I change x sub j, all of the y variable will change. But I just simply want to know how one of those y will get changed. Okay, so how do I actually figure that out? Well, the idea is to understand the following, is that when I change x sub j, what kind of impact does it have? Well, it would change u1, because u1 is dependent of x sub j. But guess what? It will also change u2, as well as u3, u4, u5, and on, all the way to u sub p. All of these variables will get changed because I simply changed the value x sub j. And how do I describe those changes? Through a derivative, of course. If I want to describe how x sub j changes u1, that will be given by the derivative du1 over dx sub j. If I want to talk about how x sub j changes u2, that would be described by the derivative du sub 2 over dx sub j. And then it continue on until how does x sub j changes up? That would be given by d of u sub p over d of x sub j. Now come the next part. If I change u1, it will definitely have an impact on y sub I. If u2 get changed, that would also have an impact on y sub I. As well, if any of the u variable get changed, they would all have an impact on y sub I. So therefore, that means now u1 would affect y sub I, u2 would also affect y sub I, and that continue on to u sub p would also have an impact on y sub I. And how do I describe those changes? Well, a derivative, of course. This change would be how y sub I get changed by u sub 1. This one would be how y sub I get changed by u sub 2. And then this continue on until the last one, which is how y sub I get changed by u sub p. And now the question is, how does x sub j affect y sub I? Well, would be affected by all of these combined together, and therefore form this single formula, which define what is dy sub I over dx sub j. And that would be equal to, let's start by examine how x sub j changes u1, which then in fact changes y sub I. And when I do that, that would be formed by dy sub I over du1, which is how u1 changes y sub I, combined with how x sub j changes u1. So that talk about how x sub j changes u1, which in turn changes y sub I. But x sub j also changes u2, which also have an impact on y sub I. So therefore I have to add that to dy sub I over du2, and how u2 get changed by x sub j, which is du2 over dx sub j. And hopefully you see the pattern here. This would continue to add up until we get to the last one, which is dy sub I over du sub p multiplied by du sub p over dx sub j. And that form a formula. Oh, maybe I use black. This form a, for how to generate one single partial derivative within the derivative matrix. Now, you might be thinking like, how am I going to remember this? Well, actually pretty simple. This is how. If you think about it, look at each of these pair of products. Notice that these two are always the same. Okay, and that is exactly how the chain rule works from BC calculus, is that you have the du in the bottom of the first derivative and the top of the second derivative. So in a sense, they kind of cancel them out. Okay. Next is that notice that you have dy sub I on top on every single one of these, and dx sub j on the bottom of every single one of these. Okay? So essentially, you're kind of adding up a whole bunch of these products where du1 cancel out, du2 cancel out, du3 cancel out, du sub p cancel out. Now, however, that leads to one of the most common misconception. So make sure you pay attention, because every year, no matter how many times I said this and tell people not to do it, some students will do it. Okay? The problem that most students have, most confusions that students have is to think of this way. Like, they would be thinking like, well, wouldn't the first product would give me 1 dy sub I over dx sub j, and then I'm adding another product that generates dy sub I plus dx sub j, and then I continue on to doing that. Wouldn't I have like multiple dy sub I over dx sub j? As a matter of fact, some students will think, wouldn't that equal to p times dy sub I over dx sub j? Because there are p of them, go from u sub 1 to u sub 2 to all the way to u sub p. That is not true. That all of these add up to only 1 dy sub I over dx sub j. And how does that make sense mathematically? It makes sense mathematically because each of these products represent only one component of dy sub I over dx sub j. The component that relating to u1, and then there's a second component that relating to u2, and then the third component that relating to u3, and on until the last component that represent up. So therefore, they are not one whole derivative. They're only part of the derivative of dy sub I over dx sub j. So when you add all the components together, it equal to one whole. So it definitely does not equal to p that many dy sub I over dx sub j. That is incorrect. It's probably one of the most common misconceptions, especially when students don't pay attention to what I'm telling them. So please don't be that student. Now I'll show you how to use this formula. And yes, once again, this formula looks massive, but it's actually very easy to use once you understand how the mechanic work out. So how about I show you using the example that we have established. Okay, suppose I have this function right here. Let f of t, which is equal to t plus 1 e to the t, which is uv, and let's say g of uv would equal to u squared plus v to the third uv, which is equal to xy. We're going to ask you to see if you can find dx over dt. So now, of course, we already know the answer to that. Why? Well, because that's what we started today's video with. Right there. dx over dt is equal to 3e to the 3t plus 2t plus 2. Okay? But how do we set up our formula that would allow us to find this? So actually pretty easy. This is how you look at it. So I'm trying to find dx over dt. So first thing you want to do is the following. Is to look at how many variable t changes. If you look at the function f, notice the output of t is u and v. 2. Therefore imply that our formula would have two components. What are the two components? This is the component of u, and this is the component of v, because t changes u and v, and that's how both of them, u and v, change x. And the way to set up your derivative formula, pretty simple. Both of these are derivative. Remember, the top of one of them is dx. The bottom of the other one has to be dt to match the derivative that we're looking for. And then the component of u would just have du. Oh, as a matter of fact, I apologize. This have to be dx and du as a partial derivative. And this become dv and dv. There you go. That's my formula. Just like that. Pretty simple. Now come the part of using this formula. So how do I use this formula correctly? Well, find all the partial derivative, multiply them in. So let's try to do that. So the way to do that is to identify how the variables are matched up. So let's learn how to do that. If f of t is equal to t plus 1 e to the t, which is equal to uv, then we can define u to be t plus 1 and v to be e to the t. And therefore, I can now say du over dt would equal to 1 and dv over dt would equal to e to the t. So I just found the two of the derivative we need. Let's do g. G of uv is equal to u squared plus v to the third, and uv, that's equal to xy. So therefore imply that x is equal to u squared plus v to the third, and y is equal to uv. Now, since we're only looking for dx over dt, we don't need all the derivative. We only need dx over du and dx over dv. So that both come from this formula. So what is dx over du? That would be 2u. But since u is t plus 1, I'm going to say that's 2t plus 2. And dx over dv, oh, I'm sorry, forgot this partial derivative, would equal to 3v squared. And since v is e to t, that becomes 3e to 2t. And now I'm ready to plug everything in. dx over dt would equal to dx over du, which is 2t plus 2, multiplied by du over dt, which is 1, plus dx over dv, which we know is 3e to 2t, multiplied by dv over dt, which is e to the t. So therefore come out to be 3e to 3t plus 2t plus 2, just like what we found before. All right, so that's how this formula works. Unfortunately, you know what, maybe I can squeeze in one more example. Let's see if we can do one more quick example. Let's say we have this one right here. Let's say I have f of xyz, which is equal to xyyz xz, and they are equal to, let's say, rst. And we have a second function, g of rst, which is equal to, let's say, r plus s plus t, r to the third minus e to st, and that's equal to uv. What if I want you to find this? I want you to find du over dy. So how do we figure this out? So once again, the same way to do it. We'll try to find out what du over dy is. So first thing I'm going to ask myself is, what is the output of the function that involves y as an input? And that will be the function f, which give out three things, r, s, and t. So therefore, I'm going to have three of these. The first one is the component for r. The second one is the component of s. The third one is the component of t. For t. Yeah, I'm going to say of t. The reason why that is the case because y does not change u directly. Y changes r, s, and t, and then r, s, and t then change u. So if you want to think about it, this is how they work. Here's x, y, z. Go for the function f to turn to r, s, t, and then go for the function g to turn to u, v. So the way y changes u, v is y changes r, y changes s, y changes t, and then r changes u, s changes u, t changes u. So that's how that works. Now, how to put in the rest of the formula? Remember, they're all derivatives, so go ahead and draw your line. Remember, the top here is du. The bottom here is dy. And then the diagonal have to be the same, and it describes the component that we want to describe. So in this case, dr, dr, ds, ds, dt, dt. Now, it should be pretty easy to find all the derivative here. So I'm going to just go for it because can't run out of time. Du over dr would actually equal to du over dr would be 1. As a matter of fact, du over ds is also 1, and du over dt is also 1. Okay. And dr over dy would actually be x. And ds over dy would actually be z. And dt, dy over dt would actually be 0 because t actually does not depend on x and y. Now, however, if you think about it, x and z, okay, that's fine. So now that would actually come out to be the following. So therefore, du over dy would just simply be equal to x plus z. And that's it. And I could definitely ask you to evaluate, but I'm not going to do that because I ran out of time. So I think we'll stop right here for today, and we'll continue some more on tomorrow's video. All right, talk to you guys later. Bye-bye.